I want to introduce you to some notation, and that is matrix notation. So first off, what is a matrix? A matrix is just a rectangular grid of numbers, and they are extremely useful. They will be the heart of almost everything we do this semester. And so one of the places that they pop up is these linear systems. And here's the idea. You can actually write down this linear system without writing down the variables, as long as you keep things in order and sort of in the right place. Let me show you what I mean. I can write down the following matrix. So we usually use this kind of side bar symbol for a matrix, and I can write down the first equation like this. I can say, well, the x1 variable has a 1, the x2 variable has a -2, the x3 variable has a 3, and then the constant that it's equal to is 0. And this is sort of the x1 column, this is the x2 column, this is the x3 column, there's an imaginary equals, and this is what everything is equal to. And so we can keep going, and we can say, well, this equation has a 0x2, and a 0x1, 2x2, and a -8x3, and it's all equal to 8. And then the last equation would be -4, 5, 9, and -9. So this is called the augmented matrix associated to our system. You can also talk about the coefficient matrix. The coefficient matrix would just be the matrix of coefficients. So it would be all the coefficients on this side, not including the constant 0, 8, and -9. Let's write it down. So this would be what, 1 -2. Here, it would just be this matrix. That's the coefficient matrix. We'll still write it down. 1 -2, 3, 0, 2, -8, -4, 5, and 9. This is the coefficient matrix. Okay, so we're going to learn, starting in the next section, how we can work with matrices to be able to efficiently solve linear systems. I do want to make just a few comments, though, on the size of a matrix before we go on. So let me change colors just so it'll stand out easier. So the size of a matrix, i.e. its dimension, is always given by is given as row by column. Okay, so the coefficient matrix that we talked about above, the coefficient matrix has dimension. Well, it's row by column. There are 3 rows and 1, 2, 3, 4 columns. So this thing has dimension 3 by 4. Oh wait, I'm sorry, I said coefficient. I meant augmented. You know what I mean. The augmented matrix has dimension 3 by 4. The coefficient matrix, now we've got it right. The coefficient matrix has dimension, well, 3 by 3. 3 rows, 3 columns. Okay, let's make one more comment just so that we're crystal clear here. In general, an M by N matrix has, well, it's row by column, so M rows and N columns. All right, so that's the information that we need. Key idea is you can take a linear system, and instead of writing all the variables down, you cannot write any variables and still capture the same system. And so that brings us to this idea of elementary row operations. We are going to simply discuss and look at 1 or 2 examples here, and we're going to dive into this a lot more serious in the next section. But I wanted to at least introduce elementary row operations to you. Let's talk about what they are. So first off, you can do these 3 things to an augmented matrix, and you won't change the solution set of the original system. You're going to get a different augmented matrix, which corresponds to a different linear system, but it's equivalent to your first linear system, meaning that it has the same solution set. And I'll try to give you a graphical demonstration of what's going on before we're done. So the first row operation is you can simply interchange two rows. You can switch the location of two rows. And if you think about it, that doesn't change the system at all. Let's just look at this system on the screen for just a minute. If I decide that I want to write that equation on top instead of on the bottom, that changes nothing. So that sort of somehow seems clear. You are allowed to multiply all the entries in a row by a non-zero constant. Let's highlight non-zero there. That's really key. You multiply by 0, you lose the equation and you've changed the system. So you can multiply by non-zero constants. So if I want, I can replace this equation with 10x1 minus 30x2 plus 10x3 equals 10. Or the line in my matrix would go from 1 minus 3, 1, 1 to 10 minus 30, 10, 10. Okay, the trickiest one is the third elementary row operation. And here's what you can do. You can replace a row by the sum of itself and a multiple of another row. So what am I saying? I'm saying you can replace this row by saying 3 times the first row and then adding it to this row. And I could keep talking about this, but I don't want to talk about it as much as do it with you in the future. So for now, all I need you to do is to recognize that there are 3 elementary row operations. You can switch rows, no problem. You can scale a row, no problem. And then you can add rows. You can add a multiple of one row to another. That's the hardest one that we're going to use a lot. And we'll see examples soon. Okay, a couple of remarks that I want to write down together. So first off, these operations. So let's just say elementary row ops can be applied to any matrix, not just augmented matrices. Okay? And 2 matrices are called row equivalent if there's a sequence of elementary row operations that change one to the other. So you are row equivalent with another matrix if you sort of came from that matrix via a pattern, a sequence of elementary row operations. Okay, and so our goal is to use row operations to replace one linear let's say to replace our linear system with an easier system to solve. And like I said, we're going to focus on this a lot in the next section, but I want to do one example of this with you. So we're asked to determine if the following system is consistent. Actually, you know what? Let's stop and do this in the next video. So we'll stop here, and then we'll do one more video and be done with this section.